We are presenting CRT6D fast 60 object pose estimation with cascaded refinement transformers, a work by Pedro Castro and Taekyon Kim at Imperial College London. We introduce a novel 60 object pose estimation method using a hybrid pipeline combining pose estimation and pose refinement in a single model. Our method achieves state-of-the-art performance when compared to real-time object pose estimation methods, while being almost 2 times faster than its contemporaries. The source code will be made available on GitHub through the link on the slide or through scanning the QR code. Given an RGB image, CRT6D starts by directly estimating a rough pose of the target object using a CNN. Seeing as a rendering of a known object with a known camera at an arbitrary pose is a representation of said pose, we propose a new representation, Object Surface Key Point Features, or OSKFs, a set of features where each element refers to a predefined surface key point. We'll show in depth how our transformer module generates OSKFs and outputs a pose offset. We take the existing set of OSKFs, or a set of learnable parameters at the first refinement step, and perform self-attention. To note that as positional embedding, we use the reproject 2D location of each point using the currently estimated pose. These attempted features will serve as queries on a deformable attention step. Values will be sampled around the reprojected 2D locations of said key points. Values are sampled at 3 resolutions from the backbone's extracted feature maps. For each key point at each resolution, we sample 4 points by deforming the reference positions. In order to output the offset pose, we then perform another self-attention step on the OSKFs, followed by a pooling operation and an output MLP. If this is not the last refinement step, we propagate the current OSKFs for the next iteration and update the current pose. We show on the bottom right 2 examples of the positions sampled by the deformable attention, the white dots, around the reference position, red dots. Seeing as our method is fully differentiable, we optimize directly for pose error. We show a few examples of CRT6D in action. Each row refers to a refinement step. We can see that for all objects, the initial pose is very poor. This is to be expected as we are using a very crude and lightweight pose estimation method for the initial estimation. However, we can see that CRT6D can, using the same features used for initial estimation, refine the pose to acceptable standards. In real-world terms, for the dataset of the first 2 columns, we achieve a translation error of less than 5 mm for over 50% of the images. Here we show detailed results for 2 datasets under the BOP guidelines. BOP stands for Benchmark for Object Pose. We also present runtime performance results. Our method, even after 3 refinement steps, is 2 times faster than the fastest of the prior methods, while being more accurate and achieves comparable results when compared to methods 4.5, 17, or even 400 times slower. Although we use transformers, our throughput is fast due to the selection of a small number of reference key points. In most of our experiments, we select 64 reference key points. This number was subjected to an ablation study presented in the paper. If compared with other visual-based transformers, it is analogous to performing attention over an 8x8 image. Performing attention on this short sequence becomes inexpensive. Finally, we share the results of CRT6D on 7 very different datasets available right now on the BOP Challenge website. It is possible to see that we are almost 5 times faster than any other method on the top 15 RGB-based approaches. This also shows that our method remains accurate even on datasets with 30 objects. Thank you.